If you have photosensitive epilepsy, you probably shouldn't watch this video. Viewer discretion is advised. Welcome to part 2 of my FPGA video card series. In this video I'll go over VRAM, ISA bus cycles, lots of bugs, and all kinds of stuff. The first thing I did was wire up the voltage regulator. Attaching surface mount resistors can be difficult to do by hand, but that's nothing compared to what's to come. I attached the resistors and what do you know, 3.343 volts. Things are off to a good start. The next step when building anything having to do with FPGAs is to attach the minimum required components that it takes to boot up the FPGA and just see if it works. In my case, this means I need the SPI ROM, the FPGA itself, and all of the other supporting resistors and capacitors and stuff. I came up with this circuit when I made that ICE40 FPGA dev board, which I ended up using as a 486 chipset. Sometimes I use tape to help hold surface mount components in place while I solder them. Most people use heat reflow, but I'm more confident in my hand soldering skills, and this is a really complicated build. Someday though, I'll have to figure out better methods if I'm ever going to be able to use ball grid array components. Eventually I finished all of this and I was ready to plug it into an SPI programmer and try it out. This brings us to the first major issue. It turns out I accidentally wired all of the FPGA voltage lines as 1.2 volts. Some of them need to be hooked up as 3.3 volts. Luckily, it turned out to be somewhat feasible to actually fix this. I figured out that if I cut several traces and added several really small bodge wires, I could make it so that the right voltages were being supplied to the correct pins. This involved removing the FPGA with a heat gun so I could fix the issue and do it all over again. The bodge wire hack was substantially difficult and I didn't get any footage of it. But here's the aftermath. Also, I got the network resistor footprints wrong, but I was able to deal with that too. So after this ordeal, I wired everything back up and turned it on. Luckily, no magic smoke came out, there were no signs of catastrophic failure, and the SPI ROM was able to function without the FPGA causing interference over the SPI bus. Now for the moment of truth. Does it actually work? And yeah, it does. Here is a gradient of red colors. Here is a gradient of green colors. Here's a gradient of blue colors. Here's every color. Here's a test pattern I came up with. It looks messed up because it turned out several of the network resistors weren't completely connected to the board, but that was an easy fix.
I did it, Cleo. Look, I got it. What do you think?
No, the audio isn't muted, it's just that this cat can't really meow. Next, I set up a SPI interface because that's easy to do in Verilog, and started using this Orange Pi 3 to send commands. Boy was this setup annoying. To make matters worse, the fastest I could ever get it to run without using a different SPI library and having to write different software was something like 111 bytes per second. Eventually, I had done all I could do without the ISA interface, and it was time to move on to a better testing setup. This here is a Socket 7 P5A motherboard with ISA slot. It can mostly run C++ OS, which is a protected mode kernel thingy that I made in C++. This is much more valuable for debugging and testing than MS-DOS or Real Mode OS, because it can straight up run GCC compiled programs. Object-oriented programming just makes things easier. It can also handle protected mode assembly. C++ OS runs without interrupt vectors or DMA, and it never touches an x86 computer BIOS, which means it can run on just about anything 386 class and higher. In fact, it could probably even run on an ARM or RISC-V machine with minimal changes, but let's not get too ahead of ourselves. Now that I have it plugged into an ISA port, this brings us to the second significant issue. The VRAM shares an address bus with the ISA port. This isn't a design oversight, It's just what had to be done to make it work on a single 144-pin QFP FPGA, since there are only 107 usable I/O ports on this version. This means that every time there is an ISA-bus cycle of any kind, the FPGA has to stop accessing VRAM while it decodes the address and figures out if the video card is being selected by the ISA bus or not. Luckily, my design with its modern 3.3-volt LV CMOS chips can do all of this in a fraction of the time it takes for the ISA bus to complete even half of a clock cycle. Of course, this opens the door to all kinds of clock domain crossing issues.
Kitty, what are you doing?
First, I tried using a FIFO buffer, but I ended up using block swapping instead. That's where the FPGA reads buffered pixel data from a 640 pixel wide even block while writing to a 640 pixel wide odd block. Each time the pixels on the screen advance to the next horizontal line, the roles are swapped. I don't doubt a first in first out buffer could have worked too, but this is easier to debug and keep track of, plus is the best and easiest method that would result in lower VRAM bandwidth when running in 320 by 240 or 320 by 200 resolutions. Since the pixel clock needs to copy pixels to the VGA port at 25.175 MHz or 50.23 megabytes per second, it needs to be able to copy data from VRAM and write them to the FPGA's internal buffer fast enough to keep up despite the ISA bus cycle address decoding system. Luckily, this circuit board seems to be very tolerant of really high speeds, so 65 MHz and beyond is no problem for it, even with all of these baud wires. However, using a 25.175 MHz clock and then an asynchronous 65 MHz clock caused too many clock domain issues to deal with. Luckily though, I found I could use a phase-locked loop to multiply the pixel clock by 3 and use that for the write buffer and the VRAM. And I just ended up with a less out of whack 75.525 MHz VRAM clock. This results in a VRAM bandwidth of 151 megabytes per second. Just making this one change obviously caused improvements immediately. Eventually I ironed things out enough that with ISA cycles disabled, the video signal was almost perfect. There is still a lot of work to be done once ISA cycles and address decoding are enabled. In order to better troubleshoot all the random flickering, I need to make it so that I can at least somewhat control what's on the screen. Here's what happens when I try to write a test pattern to video RAM. Flickering aside, that's not what it's supposed to look like. It turns out that the VRAM address counter was getting stuck on the 639th pixel of every horizontal row, and when this happened, it took an additional pixel clock cycle to start counting again. This means that each horizontal line was 1 pixel ahead of where it's supposed to be. I fixed this by incrementing the VRAM buffer write counter by 1 only once during each horizontal screen blanking period, which ended up fixing the problem. Now that I can better control what's on the screen, it's time to write some better tests. I have this one graphics mode test for VGA cards that switches to one of the 256 color 320 by 200 graphics modes, and then draws some basic text and stuff on the screen. I went into C++ OS, added a draw pixel function that's compatible with this video card, and plugged that into the same test. This is what it looks like when I run it on the FPGA video card. Running it a second time makes it somewhat easier to see, but not really. You can make out some of the fonts though. The fonts are about half the size in this test because the resolution is 640 by 480 instead of 320 by 200. I have a hunch that it isn't correctly detecting when the write buffer is full, likely due to flip-flop delay or something like that. I tried adding some delay by making the test only write to VRAM during horizontal screen blanking periods. This is done by checking status register port 426 hex and looking at bit 7 rather than bits 4 or 5. This makes things really slow, but it also removes some of the video artifacts. I needed to come up with a way to figure out if the FIFO buffer was almost full. I subtracted the write pointer and the read pointer and used the output of that to make an almost full check, and it worked in the tests I made for it, but not on hardware. I then found out if I check for the buffer being empty and incorporate that into the almost full check, then it works. This idea eventually resulted in measurable improvement. Now the pixels get written to the screen more completely than before, and it can fill the screen in almost half the time it takes if I only write during screen blanking periods. There are other opportunities to optimize and improve the write buffer, but there are more important things to fix right now. For example, if I set up a solid colored screen and write a red 255 pixel wide line starting on the second line, the glitches only glitch in white, and you can't see them. If I remove that red line, nothing different happens. But look at what happens when I draw the same red line except I do it one Y position higher on the first horizontal line. You can't see it very well on my capture card, but most of those pixels are the same color red as that line. This means the color of whatever's on that first line dictates what color some of the glitched out pixels are. This is an issue that I haven't been trying to fix for weeks with no results, so perhaps if I find the root cause of this problem, it'll fix other stuff too. I finally figured out a way to significantly reduce the random pixel flickering, also sometimes referred to as snow. The text fonts also started showing up a little better for some reason. I partly achieved this by trying different clock domain crossing strategies, mostly in the ISA-bus interface module. Doing this made the flickering and the line wobbling worse. That bug just keeps coming back in some form every time I fix it. Look, I can draw all the red lines I want at the top of the screen, and it doesn't make a lot of red pixel glitches everywhere. My blue and white test is now completely broken too. Weird. Okay, so I'm just going to stop the video right here. I don't see myself fixing all these issues within the next few weeks, so stay tuned for part 3. The GitHub link is in the video description, so if anyone has any ideas on how I can make ISA bus transfers work correctly more often than 93% of the time, or get rid of the wobble and random flickering bugs, by all means let me know. This is the file that handles the block swapping read buffer system. This is the file that mostly handles the ISA bus interface. This is the file that has the write buffer. And here's the top level file that contains modules for VGA timing sync, some more of the ISA bus interface code, and it glues everything together. You can use this file to run a test on the write buffer system, and you can use this file to run a test on mostly everything else. All of this other stuff is just experiments or things that didn't work that I just left in because I thought it would be useful someday. I just want to say thank you so much for watching. If you would like to help support future development and to enable me to continue making videos like this, consider buying me a coffee. The link is in the description.